were discussing the sample holders, how we can take the sample in different containers, and I had told you in the last class that IR cells are constructed with sealed windows which are separated by thin gaskets of copper and lead which are weighted with mercury. So, the whole assembly is securely clamped in a stainless steel holder. As the mercury penetrates a gasket, it expands, producing a tight seal. So, this is how we hold the sample. For films, how do you take the infrared spectrum? So, for polymers, resins and amorphous solids, the sample is usually dissolved in a volatile solvent and you evaporate the solvent, you will get a thin film of the material. So, a drop of the solution you can place it on the window and then seal the 4 edges. As the solvent evaporates, a thin film of a homogeneous material is deposited which can be scanned directly. For liquids and polymers, a drop of the solution may be placed and squeezed. You can just squeeze them. In case it is not volatile, you can just squeeze them and then you will get a small film like material which can be scanned for IR. Now, what about mulls? I want you to understand that the powders are more difficult to take the IR spectrum. So, powders can be examined as a thin paste or a mull. You can take about 5 milligram of the sample, very small quantities, mix it with NUJOL. NUJOL is a high molecular weight liquid paraffin, just like castor oil. So, you can take NUJOL, mix it with in a small cup, mix it with your powder and it will wet the whole thing, and you can take the NUJOL and put it on a finger and put it on the IR window and then smear it and then take the spectrum. Now, you can imagine that NUJOL being a paraffin, it will have carbon hydrogen bonds, mostly saturated carbon hydrogen bonds. So, when you take a powder, you have to subtract the peaks from NUJOL. So, NUJOL has peaks around 30 and around 2860, 1460 and 1374 centimeters inverse. So, these are the NUJOL peaks which you will have to discount when you are taking IR spectrum of the samples. Therefore, basically you cannot get any useful information about a compound which contains NUJOL in these regions, that is 3032, 2860, around 1460 and 1374. In other regions, it is useful. You can also use hexachlorobutadiene as another mulling agent, and this is better than NUJOL because it has no carbon hydrogen bonds, hexachlorobutadiene. So, you can also take a solid sample by mixing it with potassium bromide. Just take about 0.5 gram of potassium bromide and your sample and then mix it intimately and then take a small cup, and into the cup you put the mixture and then press it. You will get a very small disc. That disc you can put it and take the spectrum. You will have to press it around 25,000 psi. Then only you will get a small disc of about 10 mm diameter and 2 mm thickness. Such small handling instruments are available in the market, and when you buy an infrared, you can also buy a pellet maker. So, when you make this pellet, it gives you a 10 mm dia pellet with about 2 mm thickness. So, quantitative analysis can be performed by using the pellet technique. Now, let us discuss about the instrumentation, radiation sources. So, the most commercial instruments use an extended source close to that of a black body radiation. That is what you need basically. It must generate infrared radiation, and any black body radiation, if you heat, it will give you if you heat it between 1000 and 1500 Kelvin, you will get black body radiation containing infrared. Usually nichrome wire, Nernst Gloyer, the Opperman and the Glober sources are commonly employed as sources of infrared radiation. There are four different sources. One is nichrome wire, you can use it. Nernst Gloyer, yes, another source. Opperman is another source, and Glober source is the another source. So, nichrome wire is a simple coil supported on a ceramic rod. You would have seen even in your houses, if you take the earlier people used to heat in the kitchens using an electric stove, in which a coiled wire used to be put in the electric heater. So, the material is nichrome wire, and it is put round and round and round in the kitchen. Now, you can use a similar wire and rotate fixed on a coil, and you can use it like this. This is your ceramic rod, and nichrome wire will go like this. This is nichrome wire, and this is the ceramic rod. The job of ceramic rod is only to support. Support the ceramic wire, and it is wound around this, and it can be used straight away. Nichrome wire is either a simple coil or supported on a ceramic rod, and usually low and mid priced instruments use this. It is easy to maintain and replace. So, whenever the wire gets overheated and then gets cut, you can simply take another wire and wind it and put it in the source. So, it is easy to replace. Prolonged use definitely can lead to oxidation and thermal stresses, and that deform the coil shape. Thus, long term stability and output are affected. Therefore, you have to keep on changing the nichrome wire on and off. So, this is one source, most commonly employed source, I can say. Then another is Nernst Gloyer. Nernst Gloyer is composed of a mixture of rare earth oxides that are heated by electric current. So, you have to make the rare earth oxides and then mix them and then press them into a rod and then use it as a heater, and it is heated by electric current. This has a negative coefficient of electrical resistance. That means, most of the oxides are not good conductors. So, to make them conducting, you have to supply energy. So, its electrical conductivity increases with increasing temperature. This is what we call a negative coefficient of electrical resistance. Therefore, external heating, additional external heating is required to start the flow of electricity, and it must be carefully regulated to control a runaway situation. That means, you keep on heating externally also, and the rod also will generate start conducting the electricity. There will be resistance, it will get hot, and you should control it the temperature. So, Nernst Gloyer was also commonly used in most of the infrared spectrometers. So, the Opperman, I am coming to the third source. The Opperman, it consists of a ceramic rod again filled with rare earth oxides with a coaxial metal wire located inside the center. That means, you take a small cylinder and then fill the powder and put a wire inside that metal wire at the center. The wire is heated first, which in turn heats the oxide mixture. This is self regulating and this does not require external heating. In that way, it is better than the Nernst Gloyer. So, the Glober, the another source, is basically an electrically heated silicon carbide rod. It is a black silicon carbide rod capable of being operated at very high temperatures. In most of the cases, external water cooling is essential to help stabilize the source and to reduce the heat dissipation to other components of the infrared instrument. Typical lifespans of all these sources are about 2 to 5 years. The most common failure are the fractures in the ceramic rods or rare earth metal oxide rods, or in the nichrome wire it may get cut, or hot spot may generate, or loss of power by oxidation of electrical connections. So, these are the common problems, but they are by regular routine maintenance most of these problems are overcome. Now, let us talk about the detectors. The detectors are basically thermal detectors or photon sensitive detectors. These two are useful in infrared spectrometry. Thermal detector, there are two types, that is, one is thermal, another is photon sensitive. So, thermal detector sense the temperature changes by a change in the physical property such as generation of voltage. It may generate voltage, or it may there may be a change in the resistance, etc. The speed of thermal detectors are influenced by the thermal or heat capacity of the detector element, which is somewhat lower than the photon counting, because thermal heat sensors, there has to be some flow of the heat and it takes time, but it more than the photon counting units. But the response of thermal detector is independent of the wavelength of the incident radiations. That is important, because it is not IR wavelength dependent, it is a dependent property of the substance which you are measuring. So, thermocouple, for example, the pneumatic or GOLAY detector and bolometer are some of the detectors which belong to this class, that is thermal detectors. One is thermocouple, another is pneumatic or GOLAY detector, another is a bolometer, and IR response temperatures are of the order of about 10 raised to minus 3 to 10 raised to minus 2 Kelvin, only in that range. It is not very high. So, these are used extensively in dispersive type instruments, and bolometers are used in FTIR instruments. We will see what are these things in a short while. The thermocouple is basically two wires, dissimilar wires fabricated in such a way that they produce a they are jointed, such as antimony and bismuth. So, they produce a small voltage proportional to the temperature of the junction. So, several thermocouples are available in the market. They are connected in series for additional input. That means, you can make the changes slightly higher by using 2 or 3 thermocouples. Half of the junctions are hot, the other containing the active element. Alternate junctions are cold, that is, they are thermally bonded and bonded to the substrate and remain at a relatively lower temperature. So, you have 2 junctions, one is hot, another is cold. Thin film techniques have also been used to miniaturize these thermocouples. So, you can have very small miniaturized thermocouples and the entire assembly can be mounted on an evacuated enclosure with IR transmitting windows, because you need the infrared radiation to fall on the detector. So, the detector thermocouple must be housed in an evacuated container, which is fixed with a window which is IR transmitting. So, the conductive heat losses are minimized and the response time in such cases is about 80 microseconds. So, it should be very fast, otherwise you will not be able to scan the infrared spectrum. So, you can see in this film in this slide that this is the optical window in the IR. This is a p type n type junction and this is coated black and oxide film is here, sensing junction is here somewhere in the middle. So, these 2 junctions are connected and this is a reference junction, cold junction, and this is the hot junction. So, they are adjacent to each other, and then aluminum heat sink is there, because any excess heat must be dissipated quickly, and then all other things are fairly in place. That is, we need a window sill here, and then you need some weldings here, output signs hermetically sealed, etc. These things are more in technical nature. So, this is how a thermocouple works. Now, the wavelength response, you can make thermocouples of different materials. For example, you can make this one figure, the first one is indium antimony. This is the response at 77 Kelvin. So, this scale is detectivity is 10 raised to 8 to 10 raised to 11. This starts somewhere around 10 raised to 10, then falls off around 5 micrometers. Similarly, I have plotted here lead, tin and tellurium. This is another thermocouple. The third one is lead, tin and tellurium at 42 Kelvin, and thermistor is number 5. You can see that its response is very constant all the time, that is number 5, middle one at the bottom, and fourth one is pyroelectric material, and sixth one is thermopyle at 300 Kelvin. So, the pyroelectric, thermistor and thermopyle, they are all slightly their response is slightly lower, but they are very constant over the entire infrared region, whereas the indium antimony and then lead, tin and tellurium, etc., they are the response are not constant, but they could be they are more sensitive. So, a thermistor basically functions by changing resistance when illuminated with IR. So, you have to take the infrared radiation fall on a thermistor, then what happens? There is a change in the resistance when illuminated with infrared. So, a thermistor is also made of sintered oxides of manganese, cobalt and nickel and have a high coefficient of resistance. One of these is active, the other is coated black and mounted to increase its IR absorption. So, the reference is optically shielded, the other one is not shielded. So, one of them there is always a temperature difference between the IR exposure. Both are mounted on an insulating substrate placed on a heat sink. You have to dissipate the extra heat all the time. So, when connected with a bridging circuit, it compensates the ambient temperature drifts, that is important. So, the response time in this case is also of the order of a few milliseconds. You can note down that most of the responses are in milliseconds only. That is the requirement of infrared. So, a GOLAY, let us discuss about the GOLAY pneumatic detector. So, the GOLAY pneumatic detector uses the expansion of a gas as the measuring device. The unit consists of small metallic boxes like this, and inside that there is a gas fixed and two boxes you can connect, and then as the infrared rays fall, the gas will get heated up and expand. So, the expansion is arranged in such a way that infrared radiation is cut off depending proportionally to the amount of the expanding gas. So, this is the principle. So, the unit consists of a small metallic cylinder closed by a rigid blackened metal plate of about 2 mm square at one end and a flexible silver diaphragm at the other end. The chamber is filled with xenon. You need a xenon gas for that. The radiation absorbed by the blackened plate causes the gas to expand and deforms the diaphragm, which in turn obstructs the light path. This I have already told you. The response time in this case is about 20 milliseconds, that is almost similar to TC detectors, that is thermal conductivity detectors. The GOLAY pneumatic detector is a sort of is the best among the lot. So, this is the figure schematic figure of a GOLAY pneumatic infrared detector. You can see the pneumatic chamber is here, infrared radiation is coming from the back side from this region, and there is an infrared transmitting window, an essential part of all IR detectors, and there is an absorbing film, and this is a flexible mirror, and this one is the line grid image, grid, and then you have a photoemissive cell through which the sample radiation is collected and the infrared radiation is monitored. So, you can study this in detail, and I can only say that GOLAY cell is the best as far as my experience also goes. Now, let us discuss about the photon detectors. Photon detectors we have discussed already quite a few times, and photons incident on a semiconductor produces electrons and holes also. So, a sufficiently energetic photon raises the electrons to the conduction band. So, in a photoconducting detector, the presence of electrons in the conduction band will lower the chip's resistance, and intrinsic hole reaction pair, holes and reaction electrons, they always occur in a pair, in pairs. They are created intrinsically by raising the electron to the conduction band of the semiconductor material. Extrinsic excitation occurs, refers to the electrons raised from or impurity doped levels. Impurity, we have to dope the impurities within the forbidden band of the semiconductor. So, a bias current always is generated and the voltage registers this change as the output. So, very interesting and tricky procedure, and photovoltaic cells are also approximately similar type, that is indium and antimony metal, P and N type junctions in single crystals. The P type is laid as a thin layer over the N type. The band gap is about 0.23 volts at liquid nitrogen temperature. That means, you have to maintain the detector at liquid nitrogen temperature. Then you can use other types of detectors based on lead tin detector, telluride detectors, etc. They extend spectral sensitivity to considerably larger wavelengths than indium antimony, that we have seen the figure earlier, and that is 5 to 13 micrometers are normal, and 6 to 18 micrometers you can extend them with lead tin and telluride. When used with a current mode amplifier, response time is of the order of about 20 nanoseconds, not microseconds, 20 nanoseconds is the response time. To that extent, these things are better. So, we will not discuss more about the detectors, because our infrared spectrometry is more application oriented and rather than instrumentation oriented. There is not much you can do when you are taking the spectrum, and the expertise required is in the form of interpretation of the infrared spectrometers. So, the person who is using infrared continuously will keep on becoming an expert in the infrared interpretation. It is not possible for us to go into too much details about the applications, because as I was telling you, the more experience you get in using these things, the more expert you will be. At this stage, even if I explain to you the infrared applications, it will not be useful to you unless you personally start using the infrared spectrometry. But still, it is better to know a little about infrared applications. In general, infrared peaks occur at the same frequencies for specific groups. If you have an OH group, that is an alcoholic group, it will show you the peaks of the OH groups irrespective of the compound which you are measuring. If there is OH group, it is there. If it is not there, that means OH group is not there. So, to that extent, you can use them as pass fail test. If you see a particular frequency for a known compound functional group, then the functional group exists, otherwise it does not. For example, you can take carbon oxygen stretching vibration, that is CO group, carbonyl group, like in acetone. Its stretching vibration is the same for acetone or di-N-hexyl ketone or any other ketone. All of them should show you a carbon oxygen double bond peak, and it is different for acetic acid though, because acetic acid will have COOH group. One is CO group, another is OH group, like what we have seen here. This is a CO group, this is acetylenic group, that is carbonyl, and this would be acidic group. So, the CO group in this case in the carbonyl is slightly different from CO group in the acid. So, irrespective of that, you would see different kinds of peaks, and they will give you similar peaks, but slightly different range. where the CO group will appear. It could be due to acetic acid. In acetic acid there is an electrical effect which is predominant, and in cyclobutane there is a steric effect that is predominant. So, an IR spectrum cannot actually distinguish a pure sample from the impure sample, because if a sample is very pure, other substances are not there. That means, the impure sample may have different functional groups. Suppose you have a mixture of pure sample along with some other substances, then you cannot really identify a substance as pure substance at all. You could say only these functional groups are there, and it could be a mixture, it could be pure compound, or it could be a mixture. So, a crude product will show infrared peaks of all the reactants and side products. Even high molecular weight chemicals generally give very poor spectra. So, the progress, how you can use infrared spectrum to monitor a reaction like this. Now, for example, you can take a look at this slide. The progress of a chemical reaction can be followed by drawing an aliquot and then checking the infrared spectra from time to time for a specific functional group. The chemical separations can also be followed by the same principle. For example, here this is R1 R2 CHOH, that is a secondary alcoholic group. This reaction, this compound is made to undergo reaction to produce a ketone. So, the OH frequency is 3570 centimeters inverse for this compound, and there is no OH frequency for the ketone group. So, the CO group frequency is at 1725 centimeters inverse. So, as you proceed, this 1725 centimeters inverse appears should appear as the reaction goes to completion, and this OH frequency at 3570 centimeters inverse should be vanishing. So, this is how you can use a infrared spectrum to monitor the reaction. So, you can say that as you take the sample every 1 hour, keep on taking the IR spectrum, 3570 should decrease and CO group frequency should increase. So, the most powerful function of an infrared spectrum is in establishing the identity of a sample by comparison using the same medium. So, an unknown compound, what you can do in addition to following a reaction, suppose you want to know whether a particular compound is there or not, what you do is you have a database and compare the peaks in the same medium. So, the region of 1430 to 910 centimeters inverse, it contains lot of information corresponding to carbon-carbon stretching, carbon-oxygen stretching and carbon-nitrogen stretching vibrations and bending vibrations also. So, this region 1430 to 910 centimeters inverse is known as fingerprint region. So, even if similar compounds show similar spectra, the fingerprint region can be a definite identifying tool for organic compounds in the same media, that you should not forget. Suppose you change the solvent or something like that, then you will not be able to do this. So, another several compilations are actually available listing the characteristic group absorptions, that is functional group peaks, which can be used to characterize an unknown material. So, if a compound shows a peak around 1718 centimeters inverse, let us say, you can infer straight away that it contains a CO group, that is carbonyl group, but it could be an aldehyde such as CHO, or it could be a ketone like C double bond O, or it could be an amide that is NHCO, or it could be an ester, or it could be an acid COH group. But CO group is always indicated if you get a peak somewhere around 1700 degree, 1718 centimeters inverse. So, you need further analysis of IR spectra or other classical techniques required to identify the compound absolutely. But if the IR spectrum does not contain that CO group, you can straight away say that it is not an aldehyde, it is not a ketone, it is not an amide, it is not an ester, it is not an acid. So, this kind of information is very easily obtainable using IR spectrum. So, I have given here below certain easily interpreted absorption bands of some organic compounds. It is important to account for the peaks that are not of the analyte. For example, I have told you about NUJOL. So, we have to disqualify or not take into account the peaks corresponding to NUJOL if you are taking a spectrum in NUJOL. So, NUJOL shows at 29, 50 and 28 centimeters inverse CH stretching, and CH2 bending is appears around 1458, and CH3 we will see some of the IR spectrum containing these things, and these peaks need to be discounted while interpreting the spectra. So, this is the similar example of this secondary alcohol going to a ketonic group, and you can see that OH stretching frequency I have listed, and these frequencies must vanish, and these frequencies corresponding to CO carbonyl group and CO stretching group at 1110 1758 centimeters inverse should appear. So, similarly, you can see that in the second example, it is cyclohexanol. In CCl4, OH stretching frequency appears at 3788 centimeters inverse, and OH frequency is 3571 centimeters inverse. So, if you get these two peaks, you could infer that it could be an alcohol and saturated alcohol for that matter. In dilute carbon tetrachloride, this 3788 centimeters inverse peak is more prominent compared to 3571 centimeters inverse. So, similarly, you can see that for ketones, it is the CO group appears at 1754 to 1667 centimeters inverse, and for cyclohexanones it is 1715 to 1720, slight differences, and 1745, another is in pentanones it is 1751, but you can see that most of them are between 1715 and 1750 range. So, like this one can look for different kinds of information using infrared spectrum. You can see here that the effects of ring size and conjugated unsaturation also you can slightly discern. For example, a halogen on a carbon atom alpha to CO raises the frequency by 20 centimeters inverse. What do we mean by this is that in general, whenever we have discussed the shift of wavelength due to lability of the electrons, just like in ultraviolet spectroscopy, here also conjugation shifts the peaks to slightly lower longer wavelengths, that is reduces the energy, but it is not so prominent like in and quantifiable like in ultraviolet spectroscopy, where we have solved several examples which can be used for calculating precisely the wavelength at which the peak should appear, lambda max. Now, it is not possible to do it here, but similar effects are seen here. For example, this alpha halogen on carbon atom it shifts the peak to by about 20 centimeters inverse. So, carbonyl group in aldehydes also shifts to longer wavelength with CH conjugation itself like this, and this stretching frequency appears at 2940 centimeters inverse, whereas for benzaldehyde it appears at 2841 and 2762 centimeters inverse. There the peaks are under strain, the compound, the bonds are under slight strain. So, they appear at shorter wavelengths 2841 compared to 2940. Similarly, 3086 centimeters inverse you would see an aromatic CH stretching frequency. So, like this it is possible to generate information using infrared spectrum. For this you will have to be more familiar with the type of compounds you are handling. So, carboxylic acids anhydrides generally show 2 absorption bands. So, our good organic chemist will be able to distinguish between carboxylic acid anhydride and acids. So, because it shows 2 absorption peaks between 1870 and 1740. So, shorter wavelength would be more intense. The moment you show him a spectrum, he will say, oh, this contains carboxylic acid anhydride because it is showing 2 peaks, one of them is more intense. Like that they will be able to get information. Similarly, you can see in this slide that AC2O, that is anhydride, shows 1832 and 1761 centimeters. You do not have to remember these numbers, but as you keep on working in this area, you will be able to familiarize with the numbers much more easily than trying to remember and try to apply as and when you need. For example, in amides, you can see that 1876 and 1626 centimeters inverse range is for CO, but 1718 it appears in the vapor state. So, longer wavelength. So, in pure liquid, suppose the amide itself is a liquid, then 1650 centimeters inverse you would get a peak. Like that there are different informations, but what is interesting in this case is the last 3 lines, that is 35 to 72, the 35 12 centimeters inverse showing NH stretching. It shows 2 peaks for primary and 1 peak for secondary and no peak for tertiary amines. That means, if you suspect it to be an amide, by looking at the number of peaks in this range, you will be able to decide whether it is primary amine or secondary amine or tertiary amine. So, that is very interesting. For example, amines also show if it is a primary or secondary amine, you would see that 3570 to 3333 centimeters inverse is where NH stretching frequency occurs, and NH bending frequencies being lower in intensity, they would appear 1658 to 1608 centimeters inverse because they require less energy. So, the molar extinction coefficients of functional groups cannot be accurately determined, since the path lengths cannot be measured in infrared spectrometers. Just like in ultraviolet and visible spectroscopy, if you know the concentration and path length, you can determine the molar extinction coefficient. A is equal to epsilon Bc, where A is the absorbance, epsilon is the molar extinction coefficient, B is the path length and C is the concentration. Similarly, in infrared, you will not be able to calculate exactly the molar extinction coefficient, because the path length in between the cells cannot be exactly determined. So, but some average values you can calculate. For example, the CO group, for the CO group you can see in this slide that for aldehydes it is 500, for acids it is 800, for amides it is 1300. So, these are the epsilon values. So, for weak absorptions, more quantity is definitely required if you want to determine these substances. Then you can look at alkenes and alkaline earth materials. Alkenes would show two peaks. One is carbon-carbon double bond, that is between the range 1680 to 1620 centimeters inverse, and they should also show you a CH bond, because all the alkenes will contain CH bonds anyway, that will be appearing in the 31-35 range centimeters inverse, that is for stretching. So, cis and transforms can be identified by different bending vibrations, that is these ranges 1680 to 1620 range. So, suppose you go for alkynes, that is acetylenic type compounds CH2CH2, CHCA, CH2CH, CHCA, C2H2. So, here also you would expect a carbon hydrogen stretching bond, because it is C2H2, H2, and the CH stretching frequency should appear between 33 centimeters inverse, whereas a weak band will appear between 2275 to 2085 centimeters inverse. Similarly, another acetylenic type bond occurs in cyanides. So, therefore, here also the stretching region is same, IR region is same, but they are more intense. So, we can continue discussing like this several compounds. For example, in aromatic compounds, you can say that carbon hydrogen stretching appears a number of, gives you a number of peaks starting from 3030 to 1600, 1580, 1500 and 1450. And carbon-carbon in plane bending, you can remember that somewhere around 1000 to 670 centimeters inverse, that is near the end of the IR spectrum, you would see some CH bending frequencies for aromatic compounds. You can monosubstituted aromatic rings show very characteristic IR peaks between 750 and 700 centimeters inverse. This is a very important aspect. Suppose you are handling organic compounds with a single substituent, you must see a peak between 750 to 700 centimeters inverse. Disubstituted rings show very characteristic peaks at 50-70 centimeters inverse and 2000 to 1670 centimeters inverse. These are actually overtone bands of low intensity. So, disubstituted aromatic rings also are very easy to determine in a normal IR spectrum. Now, I want to for the sake of brevity, I want to put some of the spectrums some of the IR frequencies in this lecture, and here I have listed hydrocarbon chromophore, CH bending and carbon-carbon multiple bond stretching, etc., and ketone stretching vibration. All the things that we have discussed, I have put them in this. These are mostly available in the database. For example, aldehydes, where you can expect the peaks of 1740, 1720 and 1705 to 1680, like that. The peaks are available. This will serve you, this table serves you to quickly identify the different kinds of intense infrared peaks corresponding to specific functional groups. These are the functional groups on the left side, and these are the micrometers, that is the wavelength range in microns, and this is the centimeters inverse. So, I have put some of them for your benefit, and alcohols and phenols, etc., also are there. You should be able to differentiate between primary alcohol, secondary alcohol and tertiary alcohol. Similarly, just like what I had explained to you regarding amines, primary amines, secondary amines and tertiary amines, you should be able to distinguish using this data. So, unsaturated nitrogen compounds also I have put, that is C triple nitrogen, that is a triple bond, just like acetylenic groups, aryl nitrocyanates, isocyanates, etc. They all show you stretching frequencies between 2002 to 2070, between 226 to 2070 range. So, I think you should be able to get a quick spectrum identification using this table. Now, let us look at some of the spectra, and this is for di-N-butyl ether. Here you could see that the peaks are CH stretching frequencies are here, and bending frequencies are here, and because it is an ether, it is a neat this thing this is the CO bending frequency. So, LAURYL alcohol, it has got only one OH group and long chain molecular compound. So, OH stretching frequency you should be able to find in this region. So, I have collected some more isoborneol, and in carbon tetrachloride you can see that the range is from 4000 to 700 here, and the same thing is in microns plotted here, and what is plotted is transmittance in this case. So, cyclohexanone I have put, and cyclopentanone, you should be able to quickly see the differences between cyclohexanone and cyclopentanone. So, ethyl benzoate, again you would see number of bending vibrations occurring in the fingerprint region, that is between 1400 to 900 range, and this is a very characteristic of the substances. And this is for butyrolactone, and ethyl acetoacetate is another one I have put, and nanoic acid, benzoic acid I have put, and these things I have put so that you can correlate the spectrums what I have put on the slides. You can correlate the spectrums what I have put on the slides as well as from the table. So, that with a little bit of exercise you should be able to identify each peak comfortably. That is the whole idea of putting the tables as well as some graphs. It is only for your experience and to get a feel of how the organic compound spectra can be correlated to different substances. So, you can now I do not want to dwell more at this stage on the IR identification and IR applications, because it is an entirely different matter altogether to use the spectrum and use the IR spectrum. Our focus in this course is on the instrumentation and the applications. So, we have seen different kinds of applications with respect to spectra. Now, let us discuss a little bit about infrared gas analyzers. What is happening here? An infrared gas analyzer is basically a filter infrared spectrometer which can be used for the analysis of single components or specific components in a mixture. Suppose you have a petrochemical industry producing a polymer, then you would have spectrum of monomers as well as polymers and side products, etc. So, most of them would be in the form of gases because of their low molecular weights, and such substances in a gas mixture can they be identified quantitatively using infrared spectrum. So, spectrometry. So, for this we use different kinds of instruments, that is known as non-dispersive infrared analyzers. So, basically they are all infrared, just like filter spectrophotometers, these are also, we do not have a substance, a monochromator, which can separate the wavelengths. We are taking all the radiations generated from a single source. So, what we have here is the energy of the infrared is split into two beams. You can see in the previous slide, in this slide, that what I have here is a source, infrared source. Here is a mirror which reflects all the infrared radiation, and here I have a sample cell, here I have a reference cell. So, the sample and reference cells are different, and there is an interference cell which contains substances which are interfering in the determination, and I have two detectors here, D and D dash. So, the sample cell will give you radiation and connected to D with respect to D. So, the detector D will show you the response with respect to the sample, and detector D dash will show you response with respect to reference cell. So, both D and D dash are connected to an electrical balance circuit, but they are separated by a small diaphragm, and which can show if D is more, it will press it down, and D dash will be less. If D dash is more, it will press it up, and it will, both are in a way connected. So, how we can use this kind of information for the analysis of infrared responsive compounds in a process flow shell. The energy is actually split into two beams directed towards the bolometers wired in a balance circuit. That is what I was trying to show you in the previous figure. The sample gas flows through a cell on the top, that is it extends across the both, one beam passes through a filter cell and the other one through a compensating cell. So, a filter cell contains pure gas being analyzed, and compensating cell contains a gas similar to that being analyzed. So, for example, in the analysis of ethylene, ethane and methane, let us take the example ethylene, ethane and methane. Three wavelengths, we need to select three wavelengths corresponding to each one of them in the IR region. So, if a filter cell is filled with ethylene, all IR absorbed by ethylene will be completely eliminated from B1, that is from the detector and also from the sample. So, this is the function of the cell, interference cell, filter cell. In the previous figure I had shown you. So, how we can use this kind of information? We will take a look in the next class, that is we will talk about interference cells, non-dispersive IR with respect to different compounds, quantitative analysis, that is. So, thank you very much. We will continue our discussion on non-dispersive IR and quantitative analysis in the next class.